When I say voltage division here, that means my resistors are connected. I'll take two of them for now, R1 and R2. They have to be connected in series, not in parallel. Why? If they're in parallel, what does the voltage cross them? The same. There is no division in that voltage. It's the same voltage. So they have to be connected in series when we say voltage division. So if I have a voltage source like this, Vs, voltage source, I have two resistors. We'll do the math. We'll show you. Then I'll give you the equation. If you only have one source, the current through the source is going to travel from minus to plus, so it's going to travel this way. That's what I is. It's going to mark this voltage plus to minus, bless you, R1 times I. It's going to mark this plus to minus, Ohm's law, R2 times I. So if I do KVL here, Kirchhoff voltage law, is going to equal what? Negative Vs. I decide minus to plus to make it a minus, so it's easier on my brain. Plus I times R sub 1, or R sub 1 times I, plus I times R sub 2. Equals to 0. Well, do the math. You can factor I out. Can we solve for I? Isn't that Vs over what? R1 plus R sub 2? So what is the voltage cross R sub 1? VR sub 1. Well, we said the voltage here is I times R sub 1. So this is what I is equal to times R sub 1. That's what I times R sub 1. And that will make it what? R sub 1 over R sub 1 plus R sub 2 times Vs.
Aren't you multiplying R sub 1?
Yep, R sub 1. R sub 1 goes on the top. I just took the Vs outside.
Oh, it only goes on the top.
And if I do VR2 here, the voltage cross R sub 2, it's the same thing. You're going to end up with what? R sub 2 over R sub 1 plus R sub 2 times Vs. Notice the one thing about them, the bottom is always what? The sum of the two. If you're looking for V1 or the voltage here, it's R sub 1 on the top. If you're looking for the voltage here, it's R sub 2 on the top. So that's really what voltage division is. I'll put it in a nice clean way and I'll give you an example. If you have a source like this, and you have resistors in series, we'll call them R sub 1, R sub 2, R sub n. I'm going to call this voltage V1 because they're traveling this way, the current, plus to minus V1, plus to minus V2, plus to minus Vn. That's an n, not a 2 here, that's an n. I meant to say n. I already used 2. You get lots of them. Then the voltage across V1 is going to be, in the bottom is going to be the sum of all the voltages. R sub 1 plus R sub 2 plus R sub n. On the top, V1 is the voltage cross R sub 1, so you're going to have R sub 1 on the top times Vs. V2 is going to be R sub 2, because that's cross R sub 2, over the sum of all the voltages, resistors, times Vs, and Vn, it's R sub n That's how we calculate the voltage across each one. Now notice one thing about this. Since the bottom is the same, if the resistor has a larger value, for example, if R sub 1 is bigger than R sub 2, then you have more voltage drop here than here, because it depends on that resistor. So if this resistor is bigger than this, then V1 is bigger than V2. The bottom is the same for both of them. So the bigger the resistor, the more voltage across that. Let's take an example with numbers in it. So here's what I have. I have this actually an AC source, which means it's not a battery. It's an alternating source. Has a value of 12, so it's a squiggly line. That's why we indicate it's an AC source. 12 sine of t. We get 4 ohm resistor here. We got a 6 ohm resistor here. And we get a 3 ohm resistor here. And the question, can you find what V sub x right here? Yes? How do we find it? So I say, hell yes. So how do we find it?
Same way that you substitute voltage source for 12 centimeters. How do you do it for parallel though?
Wait, we're going to do it. You go the voltage as 12 sine? It's not, because there's that resistor here. The question, well, isn't that voltage here the same as this, which is the same as this in parallel? I go, no, these two in parallel, but not with that one, because that resistor up there. Let's look at these two. How are they connected? Now, in parallel, the voltage means what?
They're the same.
So if I combine them into one, it doesn't really change the voltage.
Right.
So let me find the equivalent of these two. And again, I can use the product over the sum. 3 times 6 over the sum of them, which is what? 9. And if you simplify that by 3, this is 1. That's 3, 1, that's a 2. So if I take these two and connect them in parallel, it says, oh, let me find the equivalent of them. So this becomes a 2 ohm, and Vx is right here. Now I can use voltage division. Notice they're connected in series. So Vx is the voltage across the 2 ohm resistor. So on the bottom is going to be the sum of these two. On the top is going to be that resistor times Vs. What is my Vs? 12 sine of t. So again, what I used equals 2 over 2 plus 4 times Vx, or Vs, not Vx, the source. And my source is 12 sine of t. Now do the math. That's a 6, that's a 3, right? 1/3, 12 divided by 3, that's 4 sine of t. And if I call this voltage Vy, what's Vy equal to? It's that resistor, which is 4 over the sum of them times 12 sine of t. This is 2/3 times 12, that's 8. And it better be 8. Why? Because when you add the 4 and the 8, that'll give me what? 12, which is what the source is giving you. The sum of this voltage plus that voltage should equal to the source, KVL. So that's 8 sine of t, and that's 4 sine of t. The bigger resistor, notice this resistor is twice as this, the voltage here is twice as that. Okay, what about current division? I'll derive the equations for you. So let's look at current division. And again, when they're in parallel, the voltage is the same, so there's no voltage division. So they have to be connected in parallel for current division. Can't be voltage division. It has to be. I'll just take two of them, just to make my life easy, but it applies to more than two. Now, if I do KCL at the top here, we have two nodes. This is ground here, which is 0 voltage. And this is what? Let's call that Vx. If the top has a higher voltage than this, that means there's a current coming down this way. We'll call it I sub 1. I sub 1. There's a current coming down this way. We'll call it I sub 2. So KCL at the top, it says all the current going to the node, entering a node, should equal all the current leaving that node. All the current entering the node should equal all the current leaving that node. What is going to that node? I sub s. What's leaving that node? I sub 1 plus I sub 2. Well, one equation with two unknowns. We know what I sub s, that's going to be given to you. What's this current and what's that current? Well, you have two unknowns, I sub 1, I sub 2. Well, if you look at Ohm's law, I sub 1, the current right here, isn't that the voltage here divided by that resistor? And what's the voltage here? Vx minus 0 divided by R sub 1, which is Vx over R sub 1. Because current's coming down is the top minus the bottom. What is I sub 2? That's this current. It's this voltage minus this voltage. So if you do these substitutions right here, equals I sub 1, which is Vx over R sub 1, plus Vx over R sub 2. Or I sub s equals 1 over R sub 1 plus 1 over R sub 2 times Vx. You want to do the math? If you want to add or subtract fractions, what do you need? Common denominator, which is R sub 1, R sub 2, right? This will be R sub 2 plus R sub 1 on the top. So what is Vx? Cross multiply. It's R sub 1, R sub 2 over R sub 1 plus R sub 2 times I sub s. I'm not interested in Vs. I'm interested in I sub 1, I sub 2. We're talking about current division. How much of the current going to go down this way and how much going to go down that way? Well, let me put this with that one. I sub 1 equals what? Vx over R sub 1, right? I sub 1 equals Vx over R sub 1. Or 1 over R sub 1 times Vx. Well, we know what Vx is right there. So it's 1 over R sub 1 times and notice what's going to happen to R sub 1. Cancel each other out. So you have I sub 1 equals R sub 2, not R sub 1, R sub 2 over R sub 1 plus R sub 2 times I sub s. Yep. And I can derive I sub 2, and if I do derive it, you end up with I sub 2 equals R sub 1 over R sub 1 plus R sub 2 times I sub s. So notice a little bit different than the voltages. With the voltages, the top was matching. When this was 1, this was 1. When this was 2, that was 2. Here, the current division, when this is 1, we're using which one? 2. When this is 2, we're using 1. Let's take an example and go through it and see if we can calculate what each value is. I'm going to take the previous example, the one we just finished, that 12 sine 2t. Remember that one? We have an AC source of 12 sine of t, not 2t, I think it was t. 4, bless you. It was a 6, I think, and a 3. And the question is going to change the question to what is, bless you, this is a 3 here. What is this current? We'll call it I sub 2. And what's this current? I'm going to call it I sub 1. So find I sub 1 and I sub 2. Not plus like physically plus, and. Find I sub 1 and I sub 2. Okay. Well, if I know the current going in this direction, we'll call it I. If I know what that current is, I'll call it I sub s, the current through the source, going through the source, is going to split into one piece this way, one piece that way. Well, a few minutes ago we said these two in parallel, they add up to what? 2. So if you look at your circuit this way, you have 12 sine of t, that's 4, that's 2, and this is I doesn't change. The current through the source is not changing. I just took these two, combined them into 1. If I take these two resistors and put them together, does that change anything? 12 sine t. I can make it one resistor. How big? 6. This is I sub s. Ohm's law says, well, the current equals the voltage divided by the resistor. The voltage is what? 12 sine of t. And the resistor is 6. Isn't that 2 sine t? So the current coming into this junction is going to be 2 times sine of t. It's going to split. Some will come down this way, some will go that way. Now this resistor is smaller than this. This will have more current. This one is bigger. This will have less current. Backward to voltages. So let's see. What is I sub 1? Since I'm looking for this current, I'm going to use that resistor. Remember, with currents backward, it's going to be 3 over the sum of them. 3 plus 6. If I'm looking for this current, I'm going to use that over the sum of them times the current coming in, which is what? 2 sine t. I sub s.
So is it the same idea, like you can only do 2 at a time though? Like say you had like a ton of resistors that were in parallel, you can only do 2 at a time for finding current.
In that case, probably what you want to do, if you have 4 of them, break them into 2 sets of 2, do the parallel for each one, find the current going to each side, then do that twice. That'd be the smartest way. What's 3 over 9? A third times 2, that's 2/3. And I sub 2, that's the current through that. I'm going to use that resistor. Uh, 6 over 9, 2/3 times 2, that's 4/3. And if I add them, what's 2/3 plus 4/3? 6 over 3, which is 2, and that's where it's supposed to be. KCL, the current entering a node, equals the current leaving that node. So that's how we do the current division and the voltage division. Sometimes you want to put all these into one problem, like simplifying, parallel, and all this when you have a bigger problem, because it does make the problem a little bit easier. Okay, let's take another example. And this is not to do with current division volt, just an example at the end of the chapter I'm grabbing here. Ready for this? So I'm going to try to use everything I know in terms of simplifying resistors, current division, voltage division, whatever it takes to solve this. Let me start with this one. It's kind of a big problem. 2 volts. When I say big, that means lots of parts, lots of components in it. $20. 10, 10, 40, 50, 20 and 4. The question, it says, compute the voltage across the 10 ohm resistors. So 2 questions. A, compute the voltage across, well, these 10 ohm resistors are connected in parallel, it's the same voltage, right? The 10 ohm resistor. And question B, the power dissipated, that means taken, observed, by the 4 ohm resistor. Those are the 2 questions. So do all the stuff you want to do. I'm going to combine everything that I know. Now I know this is equivalent to what? 1 resistor of how big?
24.
24. So I can actually do it. Nah, it's all right. I got tons of trees in my neighborhood. I'll chop them all. Here's 20. I'll redraw this just to show you step by step. 10, 10, 40, 50, and 24. That doesn't change what the voltage right here. I'm looking for this voltage. We'll call it V. That's what I'm looking for. Well, let's see. What about these two? How are they connected? Parallel. So these two will be 1 over R equals 1 over 50 plus 1 over 24. 1 over R equals what? 1 divided by 50 plus 1 divided by 24, 0.061, or 0.62 roughly. And what is R equal to? 1 over that number.
16.2.
16.2 is it? Yep. 16.2. Again, I'll go slowly with it. I'll just redraw it. By the way, these 2 resistors, how are they connected? Well, so if I combine, does that change where Vx?
No.
So it's still V here. Might as well simplify it more. What's 10 in parallel with 10? 5 when they are equal. There's the 40. And there's what? 16.2. The problems start to shrink. These 2. 56.2. And this is V.
So they're in parallel again?
They're in parallel. And remember, when they're in parallel, their voltage is not being affected. So if I take these 2 guys, 1 over R equals 1 over 5 plus 1 over 56.2. 1 over R equals 1 divided by 5 plus 1 divided by 56.2. My calculator says 0.218. That means R equals 1 over 0.218. 4.6. So now my circuit can be redrawn one more time. And we're looking for the voltage right there. And I can use voltage division now. V equals, I'm looking for the voltage across that resistor, so it's 4.6 over the sum of these 2 times the source, which is 2. So V equals to 4.6 times 2 divided by 24.6, and I came up with 0.374. Can double check these numbers. I'm the worst person with calculators.
Yep.
Volts. That's the voltage across that 10 ohm resistor. I mean, I took my time step by step. I could have done a couple of these steps in my head. I know this is one in parallel with that. So I could have done this in one step. Okay. The next question is,
Question.
yes,
If you have multiple what is it called?
sources?
Sources.
You can add them if they point in the same direction.
What if they're not?
Subtract them. If one on this end, one on that end, different story. You'll learn that next class.
Not good.
Maybe today. I don't know, maybe. Probably not today. Because we try and figure out now, combine them at the end, you have a single actually mesh here or a single node, you know?
I mean, won't you have instances where you won't be able to combine them?
Correct.
completely
Yep.
everything?
Correct. And that's where there's 6 techniques coming up in the next 3 chapters.
Mm.
Yeah. So the second part of the question, how much power is being dissipated by this one? So if you look at the circuit, you can replace it, you can cut it right there, because you know what the voltage here is. So you can cut it right there and replace that with that voltage source. So my circuit, really, if I look at it right now, for part B now, I can treat it as this circuit. I got a voltage source of 0.374. That's right here. 40, 50, and when you look at the 4 and the 20, if I combine them, does that change the current through it?
No.
Or the voltage? Well, if you combine them, change the voltage, but not the current, right? That's 24. If I know the current through that, that's going to be the same current going through this. You agree with that? Mm-hmm. The current here is the same current right there. If I know what that current, I know what the power. Power equals V times I, or I squared times R, or V squared over R. So if I know the current through this, I know what the voltage is. I mean the power. If I know the voltage cross here, I can tell you actually what the power is. Now these two, 24 and 50 in parallel equal, we just did the math, that was what? 16.2. I can find the voltage right here. If I call this V, I can get what that V is. Let's call it V2, so you're not confused here. I can get what that V2 is. Because if I know what that voltage is, I know what that current there. How do I know what the voltage here is? Isn't that voltage division again? So let me do voltage division here. V2 equals, since I'm looking for the voltage, I gotta use that resistor, 16.2 over the sum of these two times the source. And how big is the source? Steve, 16.2 divided by 56.2 times 0.374, 0.108. So I know what V2 is, which means I know what this current is. We'll call it I sub Z. Can I find that current I sub Z? Ohm's law says I equals what? V divided by R. What's the voltage here? 0.108. And what is R here? 24. 0.0045 or 4.5 milliamp. I know the current going through this. Wait a minute, let me go one picture backward. The 16, where was it, 24? Going back to this, I cut it right there. The 24 was these two, right? So the current here through this, the same current going through this. So the current through the 4 ohm resistor must be the same as I sub Z. Because these two equivalent to this, they're connected in series, they have the same current. So the current through the 4 ohm is that number. And what's the power by the 4 ohm resistor taken by it? It's I squared times R. I is 4.5 milliamp. Don't forget the milli is 10 to the minus 3. Square it times the resistor, which is what? 4. And I came up with 8.07 times 10 to the negative 5 watts. We don't like 10 to the minus 5. Can we make it 80.7? That's 10 to what power if I do that? Negative 6, right? And what's negative 6? Micro? .7 microwatts. Not a lot of power, small amount of power being taken by that resistor. Okay. Somebody asked me last class about, in digital logic, what's inside the OR gates and AND gates. And I said, sometimes you see transistors inside them. So let me throw out a circuit that's really what a transistor is. I have this circuit. This is just one transistor. 6 cosine. And this is 2300 T, 2300 T. This is a voltage in microvolts, so that's 10 to the minus 6. We have a 1K resistor here, that's 1000. We have a 15K. We have a 3K in parallel with it. And this voltage let's call this voltage Vx, plus to minus. We have a dependent current source, and the value of that where's the value? Where'd you go? 0.322 Vx and we have a resistor at the end, 3.3 kilo ohms. And the question, can you tell me what the voltage right here? Plus to minus. What is this voltage? We'll call it V out. So find V out. That's what the question is. Notice there's nothing attached to this end. So there's no current coming in from that end. Nothing. So this current coming down, where is it coming from? This current that you see, this source coming down, it's traveling this way. But where is it coming from then? Has to be coming up this way. That's the only way to come. There's nothing here, there's nothing here. So since the current's going up, it's going to mark the resistor which way? Plus to minus, backward to V out. See how V out is labeled? Plus on the top, minus on the bottom. So V out, that's the first thing. V out equals negative 3.3 K, K is 1,000, times 0.322 Vx. Do the math. It's negative 3.3 times 322, 1062.6 Vx. The K cancels the 0 decimal places here, and that's what V out is. Minus. Again, the reason is minus because the current's going up is going to mark that resistor plus to minus. Polarity wise, this is plus, that's minus, this is minus, that's plus, backward to V out. Now, if I know what Vx is, I'm done. Now let's look at these two. How are they connected? So I can combine them into one. And it doesn't change Vx. So if I look at this side of the circuit, this is what I see. I see 6 cosine 2300 T micro. 1K with one resistor here. We'll figure the value of it in 1 second. And what's the value of that? The product over the sum. 3K, 15K over what? 18K? This K cancels one of these. By 3, this is 1, that's 6. What's 15 by 6? That 2.5? Can I get Vx now? Voltage division. I'm looking for the voltage right here, so I have to use that resistor over the sum of both of them times the source. Micro. Don't forget the micro, 10 to the minus 6. So 2.5 divided by 3.5 times the 6 4.29 roughly cosine 2300 t microvolts. That's Vx. So what's V out? Negative 1062.6 times Vx ten to the negative 6. That's what the micro is. Cosine 2300 t. Do the math. I came up with negative 0.0046 cosine 2300 t. The micro is gone, so I can write that as what? Negative 4.6 cosine 2300 t, and instead of micro, this will be what? Millivolts. Notice, by the way, you put a tiny, tiny voltage in the micro, 6 micro, and you get almost 6 milli, 1,000 times bigger. And it's minus, which means flipped it, because that's a sine wave. When you have a sine wave, the graph for a sine wave is this, right? The height, 6 micro here, negative 6 micro. That's your Vs. Well, V out is going to be what? Negative 4.6. Well, actually, it was cosine or sine? I'm sorry, it was cosine. Okay. No big deal. It was a cosine, wasn't a sine. I forgot that was a cosine. I'll fix that quickly without erasing using all my ink there. It was a cosine, not a sine. Here we go. You won't even know now, huh? Creative. Tons of it, don't worry. Acres and acres of trees. So the first one, it was a cosine 6 micro. I made a little mistake here because the other one's 1,000 times bigger on graph wise. Because remember, this is 4.6 milli, so it has to be 1,000 times bigger. So I need a piece of paper the size of Texas. But what the minus sign is going to do is going to flip it upside down, right? So my outputs are, since I can't really put on the same picture, I'm going to exaggerate a little bit there. Because to use the right scale, good luck. So my output is going to be the minus, so it's much bigger than this. And it's a minus, so it's going to look like this. That's what the minus sign does. Flips it. And its height is going to be 4.6 milli and negative 4.6 milli. So what it did, it made it 1,000 times bigger, also flipped it from the positive being negative, the negative being positive. That's called reflection along the x-axis in math.